between vectors, but not exactly. So yeah, I guess you could say it is a set of, you could think of it as a set of unit vectors describing the coordinate axes combined with a set of vectors on each face of the cube.
Got it.
Okay, but remember, so did anybody have any homework questions? It doesn't sound like. Yeah.
Kind of more of a general one, but
yeah.
when multiplying two matrices of different sizes,
yeah.
What determines the size of the end result?
The number of columns on the left matrix has to match the number of rows on the right matrix, and the two dimensions that aren't involved in that are the dimensions of the final matrix.
So it'll have the amount of columns of the left, but
number of rows of the left, and the
rows.
number of columns of the right.
Okay.
Yes, that's right.
I watched a pretty good video. It's just like, you like first row, first column. You do the dot product.
Yeah.
First,
Yeah.
I don't know.
You love YouTube videos.
They're great.
I do too.
Well, number 6 was talking about uniaxial. I didn't know that.
Oh yeah. Well, it was just sort of asking you to guess, but so right. It says so if you drew the stress cubes, there was one of these that had something like the stress cube looked like this. That was the only non-zero. And there was one that looked like something like this. Those were the only non-zero.
Yep.
So uni means one, so this one's uniaxial. Bi means two, so this one's biaxial. Remember that if the stress cube looks like this, that necessarily means that that's acting on the stress cube too. You just don't draw it. You don't draw any of the hidden faces. And similarly, this implies this, but you just don't draw those two obscured ones. Oops. So this one would be uniaxial. Whether it's in tension or compression, it doesn't matter. This one would be biaxial. Any other questions on the homework? Okay. So now on each face, let me draw something before. I just want to make this clear before we stop doing this completely. And we're going to stop doing it completely because it's just so hard to draw, okay? But remember, always remember, if the coordinate system is, let's say, so let's say that the coordinate system is x this way, y this way, z this way, okay? And the stress tensor is 1, 2, -3, 2, 0, 4, 4, nope. This has to be symmetric, so -3, 4, -2. Just making up numbers in megapascals, okay? That means that the stress cube Bless you. Okay, so that means that the stress cube is lined up according to those coordinate axes. Okay? There's a relationship between, like, this stress cube always is in line with whatever the coordinate system is. Okay? You with me on what I'm trying to say there? So the x-axis comes out of this face, and the stress cube would look like, we'd have a 1 here. The y face is the one to the right, so the positive y face, so this would be 2. The z face is the top face, so -3 means this way. So this one's also 2, this one's also 3. Now I'm going to the second one. We have 0 for the normal of the y. We already have the 2. The positive 4 is in the z direction. And that means this also has to be 4. This has to be 3. This has to be 2. And the ZZ is negative. So 2 this way. Okay. So what I'm saying is every stress cube we're going to draw in this class is oriented on our picture the way that, it's always oriented the same way, and X always points to the right, Y always points up, Z always points out, just because it's so much easier to draw. But what you're really representing is a stress cube that has this relationship with the coordinate system.
That's what I was wondering, like.
Yeah.
I thought about it before, like the coordinate system, is it gonna be just based off how you kind of define it? So you can be like.
Yeah, so basically this is how we're gonna imagine it, like, from now on. So that stress cube is always aligned with the coordinate system in this way, okay? But that gets so hard to draw, okay? You'd be spending all this energy trying to figure out how to draw it. Instead, we're just gonna always imagine that once that stress cube is configured according to the coordinate system, we walk back over and look straight at the Z face, the positive Z face, okay? And so everything we draw looks the same, but we're in a different orientation.
Are you saying this is like the default configuration?
No, we'll never see this again. The default configuration
is the one
that we always do. So we'll always draw as if X is this way, Y is this way, Z is this way. And so that means that X comes out of this face, Y comes out of this face, Z comes out of this face. Okay, but remember that really what's happening is that stress cube is rotating according to whatever the coordinate system is, and we will deal with wacky coordinate systems, Did you have another question? Or
does it matter which row we'll assign to each face? It just
Yep.
depends on which direction?
It does matter. It's always, this is always the X face, Y face, Z face.
Okay.
Yep. Just like with a vector, you can have crazy coordinate systems, but when you write your vector components, your X is always at the top, your Y is middle.
Gotcha.
I have a question.
Yeah.
Would there ever be a time when we label, I guess, the stresses on the cube? Would they be like a negative number?
You can, instead of writing this 2 in this direction, I could have kept that arrow pointing in the positive direction and written -2, and that's perfectly fine. I think, to me, this often gives a little bit better image in your head of what's going on. So that's why I usually flip them around. But what you can't ever do is the deluxe model where you draw the arrow this way and put the -2, because that's a double negative and it's really saying the opposite of what you mean. Okay, so any other questions about that? Like I said, I'm never going to, again, try to draw the stress cube according to a rotated coordinate system, but that's always implied when we draw it, that it has a relationship with the coordinate system. Okay, so now the relationship between the stress tensor and the traction vector on a face. So notice that on the stress cube, you always have a vector of force per area. So every face on the stress cube has a vector of force per area acting on it. That vector is called the traction vector on that face. And we'll denote it with a lowercase t, and it's a vector. So the units are the same as the units for stress. So the SI units are pascals or newtons per meter squared. And the cool thing about the stress tensor is if you take the stress tensor and multiply it by an outward facing normal to the face that you want, it gives you the traction. So this is the stress tensor. This is the outward facing normal to the face. Let's say to the desired face. And this is the traction vector on the desired face. This works, so it works for all the faces on the stress cube that defines the stress tensor, but it also works on any inclined face. So if you want to know what the traction would be on a rotated face, this would work too. Okay, so we'll do that. But let me start with just thinking about the tractions on the stress cube itself. So let's say we have a stress cube with 10 megapascals, 5 that way, which means that has to be 5 this way, 15 this way, and then 20 this way. What's the traction vector on the negative y face? Okay, so we're trying to figure out what the traction vector would be on this obscured bottom side. Okay. Well, let's think it through first, and then we'll do the calculation and see that they match, okay? On the positive y face, the traction vector is 5 in the negative x direction, okay? 15 in the negative y direction, and 0 in the z direction. Okay, so on the positive y face, this vector is -5, -15, 0. Okay, so given that on the positive y face, it's -5, -15, 0, what would the traction be on the negative y face?
5, 15, 0.
Yep, it's all just, it's a -1 times that. Remember, that was required for translational equilibrium. And so exactly, it's 5, 15, 0. Okay, well, let's do the calculation and see that that's true. So the stress tensor for this, XX is +10, XY is -5, XZ is 0. Then symmetry, then the y is -15, nothing for z, and then for z we have 0, 0, -20. Okay, what's an outward facing unit normal? What's an outward facing unit vector for the negative y face?
0, -1, 0.
Perfect. So then the traction on that negative y face is 10, -5, 0, -5, -15, 0, 0, 0, -20, times 0, -1, 0. And so that gives you, you're taking the dot product of, so the first value, you're taking the dot product of 10, -5, 0 with 0, -1, 0. And that gives you, I guess I'll write it all out. So we got 10 times 0 plus -5 times -1 plus 0 times 0. Then for the second component, we have -5 times 0 plus -15, -1 plus 0 times 0. Then for the third one, we have 0 times 0 plus 0 times -1 plus -20 times 0. And you get 5, 15, 0. Just like we had figured.
So you can just pick a column out of there.
In this case, yeah. But now we're going to do one that's at an incline, and then, you can't do that. So this also works if the faces are at inclines with the coordinate system. So let's say that we have a face. So here's our X and Y axes. And let's say we want to know what the traction is, like basically what a traction would be for that stress tensor on this face, where this angle is 60 degrees. Okay. So what's the traction on this face? And we're going to use that previous stress tensor. Well, the first thing we have to do is come up with an expression for the outward facing normal of this face. So to do that, I'll say, okay, here's my coordinate system. I'll draw a vector like this, where this angle is 60 degrees. My outward facing normal to this face is 90 degrees this way. Are you with me on that? So the theta for this would be, you'd go counterclockwise 60, then you'd go clockwise 90. So your angle is negative 30. And so then that outward facing normal vector is cosine of negative 30, sine of negative 30, 0. And so that's 0.866, negative 0.50.
I'm having a hard time like visualizing out your drawing here. So are you like imagining the cube rotated around the z-axis?
Yeah, so it doesn't have to be a cube anymore. Like that cube, remember, is infinitesimal.
Okay.
Okay, so that cube represents loading just at a single point. Okay.
So that's like your D of stress, basically.
Yeah.
Okay.
Right. And so now it's saying, okay, microscopically, we can picture what's happening at this point this way. Okay. But now imagine that that's happening microscopically, but it's happening on a face that's at this angle. Okay. And now we're going to figure out what the tractions have to be on that face. Okay. It is complicated. I mean, but so now to calculate that, we just have to go, so the traction on that face is equal to our stress tensor, 10, negative 5, 0, negative 5, negative 15, 0, 0, 0, negative 20. And multiplied by our outward facing normal, 0.866. negative 0.50. Plug that into your calculator and you get 11.16, 3.170. This was all in megapascals, so this is in megapascals.
So what's like the physical meaning of the traction?
So it tells you kind of like the components of like pressure acting on a given face. Okay, so if this material, we knew that the stress was what we had in that stress tensor, but we knew that in our setup, one side of this material was at this angle. Then in order for that stress tensor to be accurate on that face, you would have to have a force per area going, what are the values here? You'd have to have one going in the positive x direction, so straight out this way, and one in the positive y direction, so that way. And you can use it, I mean, in complicated continuum mechanics math, you can use it for boundary conditions. You do use it for boundary conditions. We'll see that, and I'll write this down in a second, but this is the basis of where principal stresses come from that we're going to use eigenvalues and eigenvectors for. Yes?
If they're infinitesimally small, why would we need to use like faces like the one that you did instead of the X, Y, Z faces?
So that stress tensor just represents each infinitely many points along this face.
Yeah.
But this represents an actual face of the material.
Okay.
Yeah.
They're like little pixels.
Yeah, the stress is the pixels, and this is the actual, this is how you actually sawed off that material.
Okay, so you would say the traction is like a physical value then?
Well, yes.
Representative, okay.
And if in simple cases, it would represent every point along there. In more complicated cases, it might be represented by a function, you know,
Okay.
and every pixel might have a different traction on it.
Okay, I kind of get that then.
Yeah. But this is going to come back up when we talk about principal stresses. So let me write that down. So traction is equal to stress times the outward facing normal is the basis for our derivation of principal stresses. And that's coming up in a couple weeks. Justin, did you have a question?
Yeah, I'm still trying to figure out.
Yeah.
If you go up again.
Yeah.
Would it be fair to say like if that was like a block like on an incline,
Mhm.
right? So then the pressure on each individual area
Right.
derivative
Right.
on a block on an incline from the normal force pushing
Right.
up would be.
Yeah, notice that, so the way the shading is supposed to indicate is that it's kind of like the opposite of an incline.
Yeah.
You got that, right?
Uh-huh.
So the material is over here, space is over here, and that's why our outward facing normal was this way.
If you
But
multiply
yes.
the area by the force by the pressure, then that will give you the total normal force.
Yes.
Okay.
Yes. And so in a case where you did have constant tractions along this, you could multiply by the area of that face and you would know what the total force on that face had to be.
Otherwise, you'd have to like integrate over it.
Yeah.
Well, I think that's also just like how megapascals work. You need more force over a greater area to maintain the same pressure.
Yes. Yes. Okay. So that's kind of all we're going to say about stress for now. I'll give you a couple things like this to do in the homework. But now we're going to talk about what strain is. So this class really is about stress and strain. So at its kind of most big picture level, stress is the loading of a material at a single point. And in the same way stress is the loading at a single point, strain is the deformation of a material at a single point. What's the simplest relationship that you've seen between an object's loading and its deformation, like in physics 1? It's a spring, okay? And, you know, the deformation is given by X, and the loading is given by F, okay? And the relationship between those two in a spring is linear, and it's just equal to, you know, kx or negative kx or whatever, depending on your directions. Okay? So what we would love is if there was that simple of a relationship between the local infinitesimal loading at a point and the infinitesimal deformation at a point. And it turns out that there is. For the most important engineering materials, for smallish loads, there's a linear relationship between stress and strain. I mean, really, because of just thinking of things as linear approximations, you could almost say that's just a law. If you think of things infinitesimally, there's sort of a roughly linear relationship. But some materials, this doesn't work very well. Rubber, it doesn't work very well. You really can't get, it's pretty much not linear unless you're looking at such a small range of deformations. But with steel, concrete, wood, bone, lots of things, there's a surprisingly linear relationship between stress and strain that we're lucky and appreciative to have, you know, because it makes everything a lot easier. So what do I mean, smallish loads? Well, eventually, I'll show you graphs and stuff of this, but eventually you get to the point where you get to permanent deformation, and then things start looking nonlinear. But the good news is in engineering applications, usually you're trying to avoid those permanent deformations anyways. And so this linear region for engineering materials is a very useful region. And so this range of possible loads that you can subject engineering materials to is very useful and very easy to calculate these relationships because of the linearity. Yeah.
So all materials are springs until they're not? Is that?
Yes, yes, all of the most important engineering materials are springs until they're not, but like rubber really is never a spring very usefully, you know. Polymers, any kind of polymers are pretty much never a spring, but bone, steel, whatever. I mean, it kind of makes sense. Like a spring is made out of metal, right? Like it's going to be getting its properties in some way from the properties of the metal, you know, and it's just shaped in a way that elongates the amount of deformation you can get from it before permanent deformation happens. Any other questions about that? So what does it mean that there's a linear relationship between stress and strain? It means that there is a matrix. So when you're talking about 3 dimensions, it means there's a matrix relationship with constant element values. And this is just something to keep in mind as you go through the calculations. When you see strain values, you want this to trigger your brain to ask, is this a realistic value or not? So we're talking about engineering materials. So for engineering materials, in their linear, or if you want to try to make yourself sound like a big shot, Hookean, you know, like Hooke's law, in their linear region. That's the linear range of deformations. Strain values should be less than about 10 to the minus 4th. Okay, so I'll give you some mathematical examples to work through, and sometimes those values will be bigger than that. And you want that to trigger in your head, like whenever you see a value for strain bigger than this, you want to think like, okay, that's not realistic. If I'm using this in a realistic description of steel or whatever, this should be a major red flag. Okay. What?
Meters?
Oh, good question. Strain we're going to see is unitless. So it doesn't matter what units you're using for stress. Strain is always this, because we're going to define it as like a deformation divided by its original length. Okay, so you can think of it as kind of like that's like a fraction of its original length that it's deformed
so
in some way.
Ratio of deformation to its size.
Exactly. Okay, so we're going to start by talking about, before I do that, so here's what a deformation is. So if this is the undeformed infinitesimal cube that defines a point, okay, so this is like the infinitesimal undeformed point. And then it undergoes a deformation. And that deformed shape is going to be a parallelepiped. So a shape that's made up of parallelograms. So it undergoes this deformation. And its deformed shape is a parallelepiped. That means the sides are parallelograms. Well, since we just talked about the fact that the meaning of strain is has something to do with the deformation divided by the original length, you can see that anything you can visualize like this is way, way more than strains of 10 to the minus 4. Okay, so this is not realistic. I mean, you can imagine, like, if you tried to do this to steel using some kind of hydraulic press or whatever, that steel is way, way past its ability to return to its original shape. Okay. Okay, so there are two things that happen in this deformation. Those are length changes. And those are going to be defined by the normal strains. And angle changes. And those are going to be defined by the shear strains. So I'm going to start by talking about the normal strains. And so we're going to go from a shape like this that has original side lengths of capital L0. And we're going to go to a deformed shape. I'm making it super exaggerated, where the x length changes to a lowercase l sub x. The y side changes to a length of lowercase l sub y. And I'm going to define my normal strains. I'm always going to denote them with the Greek letter epsilon. And my XX normal strain, you can just think of that as the normal strain in the x direction, is equal to Lx minus the original length, so that's the change, divided by the original length. And you can see from that definition that this is unitless. And EYY, the normal strain in the y direction, is Ly minus L0 divided by L0, unitless. And in this figure, this is a two-dimensional drawing, but so you don't see any deformation in Z, but you could imagine that being defined just the same way. EZZ is equal to LZ minus L0 divided by L0. And from these definitions, this is the last thing I'll say, and then we'll stop. Notice a positive normal strain so normal strains, we're talking about length changes. Look at the definitions of those and tell me, is a positive normal strain the material being stretched or contracting? Stretched, yep. So positive normal strain always means the material is stretched. Negative normal strain always means that it contracts along that axis. And notice that everything we've defined so far, going back to statics, going back to internal loads, internal tension in statics, they all agree with each other on this point. You know, a positive internal tension in statics meant the material is being stretched. A positive normal stress means the material is being stretched. A positive normal strain means the material is being stretched. Okay, and the opposite is true of negative values. Okay, that's all.